This is the first exploration of content in this really mysterious chapter, Chapter 6, Understanding Significance, where we wrap our head around some confusing ideas. But I think they'll make sense to you after this. We're going to start by talking about type 1 error and type 2 error. And these are some key topics that we'll cover. So we're going to use an earlier metaphor, innocent until proven guilty, which is a metaphor we used when we were first beginning to talk about hypothesis testing. And so let's imagine that this is the scenario. This window is broken and there's this child with a ball. And he says, "It wasn't me, I didn't break the window." And So we have two possible truths. And the actual truth, we can never know. Maybe this boy is lying, maybe the boy is telling the truth. We will never have a way of knowing. Let's assume that, because in research that's always true. And it's also true in situations like this. So here's our boy. "It wasn't me, I didn't break the window." So maybe the actual truth, the thing that really happened, is that this boy is innocent. He really didn't break the window. Maybe that's the truth. Maybe this boy is guilty. Maybe he really did break the window, and maybe that's the truth, and we cannot know. So now, in this case, the mom, the judge, has to make a decision. Should I believe this boy? She could make the right decision, or she could make the wrong decision. So here we are with these two possible decisions, and we know that the decision can be right or wrong. So here he is, he says he didn't break the window. We'll never know whether he did or didn't. And maybe she makes the decision that he is innocent. Maybe this mom or judge, whoever it is, concludes that, yep, he didn't break the window. Or maybe she makes the other decision. Maybe she concludes that he's guilty, decides he did break the window. Either way, her decision could be right or her decision could be wrong. It could be consistent with what actually happened or inconsistent, and she just has to do the best she can, making the decision about whether or not to believe him. So in science, these types of decisions where there's a truth that we can never know and it may be aligned or misaligned with our decision, that's called type 1 or type 2 error. So in this case, how well does mom's decision align with the truth, with what actually happened? And so we know there's a truth out there. Either the boy broke the window, yes, he really did it, or he didn't break the window, he's innocent, he didn't do it. We don't know. We will never know. Let's assume that. And then mom has to make a decision. She has to decide, yes, positive, he did it, or she has to decide, nope, negative, he didn't do it. So let's look at these. First off, if she makes the decision that he did it, and that's the truth, he really did do it, then there's no error. She made the right decision. There's a chance that'll happen. Or she could decide, make the no decision, negative, he didn't do it. And in truth, he really didn't do it. This is following these two lines down. That could happen, and that could be the right. And we want one of these two outcomes. We want the decision to be aligned with what's actually true. But since we'll never know, there's always a possibility of error. And the first type of error is called a type 1 error. It's a false positive. It would happen in the instance that she decides he did it, and in reality, he didn't do it. She falsely accuses him, judges him, condemns him, punishes him, and maybe, he ends up having a punishment, and maybe he has to spend his money to fix the window, and maybe people stop trusting him or feeling he's responsible. So there are some consequences of this error. Alternately, she could make a type 2 error. She could decide that he didn't do it, assume him, believe his word, and then actually he really did do it, a false negative. In that case, there could also be consequences. He starts to think he can get away with things. Maybe he lies more often because he finds it benefits him. Maybe some other child actually takes responsibility for breaking the window and gets punished. So there are consequences of this error too. And so the researcher is always trying to find a balance. Which type of error would be worse? And that's what the researcher decides when they do things like setting alpha or setting the significance level. So now let's take this metaphor into research. So in research, we also have two possible truths, and the actual truth is always unknown. We'll never know for sure because we're working with probabilities. And so there is a truth out there somewhere that we'll never know. And the question is, does the medicine work? Does it cure the illness or not? Right? That's the question the researchers are always asking that we'll never know the answer to. And there's a possibility, yes, that the medicine cures the illness. That's possibility one. And possibility two is no, the medicine does not actually cure the illness. So either of those are the truths that could be true. The researcher's trying to do his or her best to detect which of these truths is true. And so the researcher has two possible conclusions. Of course, their conclusion can be right or wrong. And so possibility one, yes, the researcher concludes that the medicine cures the illness and starts marketing, selling the medicine. Or possibility two, the researcher concludes that the medicine does not cure the illness and throws it in the trash. So we also have type 1 and type 2 error in research, answering the question, how well does the researcher's decision align with the truth? And there is a truth out there, either yes, positive, the medicine actually cures this illness, or no, negative, the medicine doesn't actually work. It doesn't actually, in real life, cure that illness. And of course, the researcher must make a decision, because he'll never know the truth. Make one possibility, yes, positive. The researcher rejects the null hypothesis, concludes the medicine cures the illness, and starts selling it. Or possibility two, the researcher could decide, nope, negative, fail to reject the null hypothesis, conclude the medicine does not cure the illness, and throws it out. So we could have a situation where there's no error. The researcher says, yes, the medicine works, rejects the null, and actually, in truth, the medicine does work. That would be great. Or we could have another kind of no error situation. Possibility that the researcher decides the medicine doesn't work, fails to reject the null, and in truth, the medicine doesn't work. So again, the researcher made the right decision. But since we'll never know the truth, there's also the possibility of error. And there could be a false positive. The researcher could, decide that medicine works and start selling it, but in reality, it doesn't work. It doesn't cure the illness. Bummer. One type of error called type 1 error, also known as a false positive. Another type of error is a type 2 error, a false negative. The researcher fails to reject the null, and there it stands. He decides the medicine doesn't cure the illness and throws it out. It's gone. But in actuality, the researcher missed it. The medicine actually does cure the illness, and that's our type 2 error in the sciences. This is that balancing act that the researcher has to do as they're proceeding with research. They have to make the right decision setting up the study, and again, they base it on which error could be worse. What type of error would be worse if they made it? And then they set up conditions to minimize the size of that error. So the researcher has to make a big decision whether to reject the null hypothesis, and the decision has consequences. So consider the hypothesis. Dr. Safe hypothesizes that people who take a particular vaccine shot will be less likely to get COVID-19 than the general population. So population 1, people who get the shot, are being compared with population 2, people in general. The likelihood of getting COVID-19 is what's being measured for the dependent variable. For the tails, we're looking at a one-tailed low test. The research hypothesis, I've just written it in shorthand for now, don't worry about that, is that the mean for population 1, those who get the shot, will be less than the mean for population 2, and the null hypothesis is that there's no difference between these two groups. And since we're doing a one-tailed low test, we need to just indicate that there's going to be some sort of a cutoff point down in this region, and that anything in this area below the tail will allow the researcher to reject the null hypothesis, and conclude that the vaccine works. And if we have anything in this area, we have to fail to reject the null, the researcher might throw the medicine away. And we're pretty familiar with this by now. So the possible outcomes then, there is this truth. In reality, one of the following is true. Either it works or it doesn't work. And of course, the decision we're going to make is based on probabilities. So the odds of a particular score falling in this tail represents the chances that we're willing to take about making a type 1 error. Alpha is related to type 1 error. So we'll just write this here, and let's fill in this alpha. Oh boy, I keep grabbing the highlighter by accident and changing the color on it. So let's make this decision based on alpha. Whatever we decide there also refers to the likelihood of type 1 error. So maybe this would be 5%, maybe this would be 1%. Either way, that's a decision the researcher has to make. How comfortable are they with type 1 error possibility? Possibly they'll make a mistake. Ideally, we're not going to have any error. We're going to have the researcher's conclusion being aligned with truth. If there's no error, it's a true positive, the researcher would find a significant difference when the difference really does exist, conclude that a medication works and the truth is that it does work, or a true negative, conclude that the medicine doesn't work and the truth is it doesn't work. So once again, the decisions are based on significance levels. Larger alpha is a greater chance of type 1 error. And so if we decide we're going to put alpha way up here for some reason, then we're deciding, you know, if we make this mistake, a type 1 error, false positive, it doesn't matter much. Whoops, I did that same thing again with that pen. So this is type 1 error likelihood. And this is represented by alpha. And you know we usually use 0.05, 0.01, 1% we're comfortable with, 1% chance of error, or if you're doing really, really serious research that might relate to life and death situations, maybe you'd set it to 0.001, you have that very, very small chance of type 1 error that you're comfortable with. So that's one way that you adjust your comfort level with a false positive. So the kinds of things that the researcher considers are how bad would a type 1 error be? And so if the researcher concludes, makes a false positive and concludes the vaccine works, but it actually doesn't work, what's the harm? Well, maybe there's a population impact. Vulnerable people might get that vaccine and feel protected and then expose themselves to the virus and become very ill or die. That would be bad news, a false positive. There could be a financial impact. Federal money would be wasted on a bad vaccine. That's a bummer. We could have used that money elsewhere. But the drug company would make a lot of money, so that could influence, some of this decision, possibly, hopefully not. And then there's a personal impact. Since the truth may never be known, if the researcher puts forward this vaccine and publishes a paper and so forth, well, they might have more success in their career. So, these are all the things and many more that might get weighed out. And so what do we do about this? Once again, I'm repeating some things I already said. The probability of making a type 1 error is alpha. How could this happen? How could a type 1 error occur? Well, if we're testing a sample, it could just happen by chance that we get a group that responds really strongly to the vaccine. So remember, all of these are possible samples, and we're just looking to get a sample in this tail of the distribution? Well, you know, if we draw 1,000,000 samples by chance, just draw them at random and we don't even give them the vaccine, 5% of them, same thing again, I keep doing the same blunder. Let me get my pen here. 5% of them, 5% of samples chosen at random with no vaccine will fall in the shaded area. That's just the nature of probabilities. That's how these errors occur. And so if we set alpha to be lower, if we set alpha to be, let's erase all of this, and if we set alpha to be much lower, let's say we set it way down here, maybe the 1% level. Let's say alpha equals 0.01. Now we're looking at these symptoms of illness, and everyone in this shaded region, we're going to conclude that the vaccine works. If our sample who take the vaccine get a score in that shaded region, we're going to conclude that the vaccine works in the end. And in this case, we know that even so, we could make a mistake because we know that just because of the nature of probabilities, 1% there we go, 1% of all random samples will fall in the tail, even if they didn't have the vaccine. So this is the kind of thing that how mistakes can occur, and that's why we set alpha to be really low if we're concerned about type 1 error. How do we avoid it then? We set alpha to a really low significance level. If we think type 1 error would be the bigger problem, then we set a low alpha. And a couple other ways we'll learn about later are we can change the sample size, make sure our sample isn't too large, and we can also predict larger effect sizes. That's another way. So all of these things impact the likelihood of type 1 error. So how bad would a type 2 error be then? False negative. How bad would it be to conclude that the vaccine does not work, but actually it does work? What's the harm? Well, there could again be this population impact. People could become ill or die because they couldn't get a vaccine, but in reality the vaccine would have saved them. So there's a population impact. There's a financial impact. You know, maybe the drug company would pull its funding from the university and, you know, things like that. And then there's a personal impact for the researcher who might give up and stop this work, and maybe that work would have been really important to the future of medicine. So that's the problem with type 2 error. And so type 2 error is a false negative. Once again, repeating this, and I'll introduce you later to this term beta. That's the probability of making a type 2 error. Alpha is type 1 error, beta is type 2. How could that occur? Well, the same thing could happen. We could choose that random sample. Nothing is ever perfect, and just by chance, we get a group that happens to fall into instead of falling into this tail, just by chance, because of idiosyncrasies of the group. Let's get that highlighter out again. Just by chance, instead of maybe their symptoms were reduced a little, but not quite enough, and so this particular group, just by random, happened to fall into this area instead of into the reject area. And so how do we avoid it? We do just the opposite. We set a little bit higher significance level. So if we think type 2 error would be the bigger deal, then we would use a higher alpha, possibly. Or we could also have larger sample sizes, which impact type 2 error, and smaller effect sizes impact type 2 error. So let's take a look at a couple of little problems. Here we have Coronata. She developed a virtual reality game that she thinks are going to help people overcome social anxiety. She analyzed her data, rejected the null hypothesis using alpha at 0.05, and concluded that social anxiety really was lower for people who played the game. The truth is consistent with her conclusion. What has occurred? Is it type 1 error, type 2 error, no error, it's a true positive, or no error, it's a true negative? And in this case, it's a true positive because she rejected HO. She made a positive decision that the virtual reality game works, and the truth is that it did work. So there's no error, it's a true positive. A second example, Dorian conducted a study to see whether people who turn off their cell phones for 1 week have less anxiety than people in general. Her statistical test caused her to fail to reject the null hypothesis and conclude that there is no difference in anxiety between people who do and don't turn off their cell phones. The truth is that turning off cell phones for a week really does help reduce anxiety. That's the truth. What has occurred? Is it type 1 error, a false positive, type 2 error, a false negative, no error, true positive, or no error, true negative? And in this situation, she failed to reject. She drew a negative conclusion. It doesn't work. And it was the wrong conclusion because it did work. So this is a type 2 error, a false negative. These are the kinds of questions that are in the practice quizzes this week, so you can play around with this and see how you're doing. I just did make a couple slides here so we could lay this out if needed, but I don't think we actually need to. You'll see it here if you need it. And one more couple examples. Dr. Hanna predicted that a medicine would help people with patience. And the truth is that the medicine works. However, because of an anomalous sample, just a weird sample that just turned out that way, he failed to reject the null hypothesis and concluded that the medicine did not work. What has occurred? In this case, we have a negative conclusion. He failed to reject the null. And in fact, though, the truth was that the medicine worked. So here again, we had a type 2 error, a false negative. And let's do one last example. Kermit the Frog hypothesized that his monologues about being green would increase children's self-acceptance. But the truth is that the monologues don't work. It doesn't make any difference on children's self-acceptance. However, the statistical test led him to reject the null hypothesis and keep on talking about being green. What has occurred? Well, in this case, he rejected the null hypothesis. He thought that this monologues about being green were actually helping. But in fact, they don't work. They don't work. So the truth is they don't work, but he said they do work. This is a type 1 error, a false positive. He made the positive decision, and it was wrong. It was false. And once again, I did lay this out here in the grid so you can see what that looks like. So finally, let's just look at a couple other questions that maybe we'll talk about in discussions in class if we have that opportunity. Imagine that you have a treatment that's promising as a treatment for long-term alcohol addiction. Which would be more serious, a type 1 or a type 2 error? Isn't that a good discussion question? Would it be better to put out a treatment that you say works and in truth it doesn't work, but you think it does? Or a type 2 error, you develop this treatment, you hope it works, but then you look at the data and say, it doesn't work, but really it would have helped. Which one would be worse? Another example, you're a juror in a trial of a man accused of murder. Which would be worse, type 1 or type 2? What about this? You're interested in whether active listening, like a therapist, active listening practices improve outcomes for people seeking therapy for the first time. Which would be worse, to conclude that it works and then it doesn't work, or to conclude that it doesn't work but it actually works. And finally, you hypothesize that women who go through the Canal d'As ceremony have stronger self-respect as women. Maybe we should say girls there because they're girls when they're going through that ceremony. Which would be worse, type 1 or type 2 error? And so that's the end of this lecture. I hope you found it interesting and helpful.